maybe let's start. Yeah. So, well, it's a pleasure here. We have today Vincent. First, thank you for waiting this half an hour. We had some problems of communication in the transportation system of Barcelona. Finally, we managed to come here. So Vincent, it's great to have here him today. He usually PPFL, recently he moved at Graz, and he used to work in descriptors, but as everybody now, he's also working in deep learning. So I guess you have heard about this, but Vincent will present something on deep learning and 3D methods, right?
Yeah.
Okay, so all yours.
Okay, so we start by I'm sorry. With a very bad joke and saying that I deeply apologize for the delay. I trust Google too much and I went to the wrong place. Okay, again, I'm just very sorry. It's entirely my fault. So yeah, so we'll talk about deep learning and deep learning for hand pose estimation. So maybe you saw this video from Microsoft. So it's a file for this video about the HoloLens, so which is this augmented reality glasses developed by Microsoft, and so they want to develop augmented reality applications and especially video games. It's not completely clear from the video what is actually done technically, because it's difficult to understand what is fake, what is a mock-up, and what is really working. But at least we know that one of the problems they want to solve, one of the things they want to do is to let the user interact with the virtual objects from using just the glasses of so the augmented reality glasses. So they want to get a precise estimate of the pose of the hand, so of the users from a camera which is on the glasses. And so that means that they would like to, and we also would like to do that, to estimate the 3D pose, the 3D locations of the joints of the hand. So that's to get really a precise estimate of these points to let the user interact very precisely with the virtual objects. So that's a Minecraft game, but that can be anything. So we want to do the same thing as Microsoft, so which is a bit scary because they have a lot of brilliant people and brilliant researchers, brilliant engineers. But the good news is that there was a paper on arXiv published 1 or 2 months ago by actually people from Microsoft, where they compared several methods for exactly that, so for hand pose estimation. So they re-implemented our method, and actually we are there, so which is nice. So we get pretty good results. So that's where we come first in their comparison on their dataset, and it's an independent result. So that we implemented our algorithm. So it's their code and still working, so which is good news. It's also because it's easy to re-implement. I will try to show that it can be done pretty easily. So the good thing is, so if we want to work in this area, is that there are already several data sets that we can use for testing and actually for training our method, because we are going to use learning, so machine learning method. And so typically these data sets are from 3D depth cameras. There is one famous data set which is from the Kinect, so to a structure, maybe it's not the Kinect itself, but it's a structured light with the same technology, and so it looks like that. So there are some artifacts, but it's a 3D camera, and so that's from a time of flight camera. So there are a little bit less artifacts, at least less visible artifacts. But the good news is that we have access to a lot of images that are Lepetit that we can use for training, except that there is a lot of noise in the annotation. So the evaluation, the training and the evaluation is sometimes difficult, but it's very difficult to get accurate locations for the hand for trading. It's not clear how you can generate these data. So we are going to use depth cameras, so that's going to make the problem much simpler than with the color, just with the color camera, but that's still difficult. That's still challenging, so there is a lot of self-occlusions between the fingers and the palms of the hand. It has a lot of degrees of freedom because that's so the parameterization that we are using is just the 3D location of the joint. So for each joint of the hand, we have three coordinates to estimate. And there is a lot of self-similarities. All the fingers look more or less the same, so it's easy to make a confusion. So the input is noisy because that's the depth cameras, especially with the structured light. There is a lot of artifact still. And so just to show you one video, so I hope it's not going to crash. So that's the comparison with the state-of-the-art and our method, so that's a still frame. And so, as I said, it's easy to make a confusion between different fingers, and sometimes so this method, which was using randomized forest, so they can put two fingers at the place of an actual one. So that's yeah. So again, there is a small mistake on the pinky, and we get it. Yeah, and quantitatively, we're also more accurate. So yeah, so I apologize again. So we'll use we're using deep learning like everybody else. I prepared a few slides to introduce deep learning because actually it's not that difficult. If everybody is familiar, I can skip them, or I can. So it's a matter of 6 minutes. So who wants me to present this slide? So who is very familiar with deep learning? Okay, so it's more or less half of the audience. So I will give a 5-minute crash course in deep learning, and because it's simple, you see it's almost enough. So to start. This presentation or the course, I will start with the standard neural network that you probably already know. Typically, the representation, so the visual representation of a standard neural network is like that, but I always found this representation confusing, and actually maybe the mathematical notation is clearer. So the output of a layer of neurons can be written this way. So it takes as input just a vector. There is a linear transformation of this vector. So M here is a matrix. So this product is, of course, just a vector. And then there is a non-linear operation, which is so typically traditionally in the neural network literature, a sigmoid, so just a function like that. And so because it's non-linear operation, we can chain several layers like that, and that's where the neural network gets its power. So just to be clear, so the sigmoid is applied to a vector, it just means that it's applied to each coordinate of the vector. So that's a standard neural network, which is something which is pretty probably as old as machine learning and computer science. So the first thing that was done, or actually it's not really the first thing, that's the simplest thing, which makes probably the new neural networks, or the deep learning, the deep networks work now, is the change of the non-linear operation. So before, people were using a sigmoid, but it makes everything difficult because the gradient can be flat here, and it's actually the sigmoid makes everything difficult to optimize. And there is with just a small change. So instead of taking the sigmoid, people now use the ReLU operator, which has this shape. It makes everything much simpler to optimize. So a gradient descent works much better. So that's the first transformation. And actually, so what I presented that is now it's called in the jargon of deep learning, it's called a fully connected layer. It's typically represented this way, but it's the same as a standard neural network or a layer of a standard neural network with the ReLU operator. And it's represented this way because it's simpler. Then there is a second type of layer, which is actually just a specialization of this type of layer with the linear transformation, which was done before with the matrix. To apply that to images, of course, with the matrix, that would be too hard. It becomes untractable very quickly. So we can actually replace the matrix product by product of convolution with these filters. Instead of using a matrix, we can use a bunch of filters, which makes things easier to apply to images. And so now the input can be an image of this new type of layer, and the output can be several images. So one image as output for the filter. Actually, it's easy to generalize that to take not just one image, but several images as input. And so the input can be a set of images, the output is also a set of images, so we can change these transformations. And there is a third type of layer, which is the pooling layers, which is the equivalent of the histogram in SIFT, for example. And what this pooling layer does is to replace the values in one region of each region of the image by a single value. So, for example, by taking the maximum value in this image and keeping only the maximum value. So the advantage of this type of layers, there are at least two. So like the histograms in SIFT, it's a way to become invariant to small shifts in the image. And it's also a way to reduce the dimensionality of the problem. So we can have large images as input and get much smaller images as output. And it's also a way to make the problem more tractable. And then we can change all these different type of layers together. So typically we can change one convolutional layer, and then a pooling layer, and again a convolutional layer, and a pooling layer, and with fully connected layers. But the structure of the network is free, so you can take it as you wish and as it adapted to your problem. It's very flexible. So for example, for what we are going to do, the input is going to be an image. So we change these convolutional pooling layers, and the output is a vector which is made of the 3D locations of all the joints of the hand. And then, so we need to estimate the parameters of the network, which are the coefficients of the filters, for example. So the filters of the convolutional layers, and of the weights of the fully connected layers, so like neural network. So these coefficients, so all the parameters, the coefficients of the filters and so on, are optimized by minimizing an objective function that can look like that. So again, it's very flexible. We can use any objective function that makes sense. And so it's a big optimization over all the parameters of the network and over a training set. And so, for example, we can compare the output of the network with the expected output for each sample. But again, it's very flexible because we just use the stochastic gradient descent to do the optimization, so we can take any form of objective function. So of course there is a lot of tricks to do the optimization right, because there is a lot of parameters and so on, but that's techniques that are getting to be known, well known now. And so there is a lot of libraries, actually software libraries, that you can use to do the optimization. So okay, so that's the end of my crash course. So that was more or less 5 minutes. So I hope that it was clear. Yeah. So that's, I think you know all the basis of the basics to use deep learning. Do you have questions on that? Was it clear? Nice. Yeah. So we'll show how we can apply that to estimate the position of the, or to do the pose estimation of the hand. So we are going to use a training set of many images, of depth images for which we know the 3D pose of the joints. So during the training set, we optimize the parameters of the network, and once we have that, so we can apply this network to a new depth image, and to get a vector which is made, at least in our case, of the 3D locations of the joints of the and actually, so the first thing to try is to apply directly a standard neural network, or a deep neural network, to this problem. And so that's, of course, we started with that. And actually, we already get good results. So not good enough for publication, but at least it's very encouraging. So a straightforward deep network does something which is not too bad. So that's the representation, or that's a curve which is used in the literature to evaluate the quality of the results, and it's a very difficult measure to optimize because that's so on this axis that's the distance, that's the distance threshold. On this axis, so that's the percentage of the frame for which all the joints are below the threshold compared to the ground truth. So it's very tough. It's very difficult to get to be there, because to be in this part of the graph, you need to have all the joints right and so below the threshold. So it's a difficult measure. So what we get with this first network is something that looks like that. So in blue, that's the ground truth, and in red, that's the position of the joints that we get, at least for this example. So it's not too bad in the sense that it's close, but it's a bit weird. The pose that we get, so the pose in red is not natural. So that's what is interesting to notice, and we are going to try to predict natural poses. And so that's the advantage of being old. At some point you get some experience, and you can reuse old work, so there is actually a long literature on hand pose estimation, and people were already using a long time ago. Yes, so now it's already a long time ago. Priors and embedding to enforce priors on the pose of the hand. So I will explain how we can adapt this kind of work to this new trend of machine learning. And so, for example, to learn a prior on this type of data, so on the pose, we can use something, a special type of network, so which is called Autoencoder network. And the idea is very simple, actually. So it's shaped like a diabolo, so that's something like that, and then something like that. And so it's unsupervised learning. The input in our case is going to be what we want to predict, so the pose of the hand, so all the 3D locations of all the joints. The output is also going to be the same vector, and then there is some kind of bottleneck in between. And we train this network so that the input is the same as the output, or the output is the same as the input, but there is a bottleneck. So that means that the network is forced to learn a compact representation of the input to be able to generate the output right. So that's it's a way of compacting the data. And so the way it's done, so it's the ReLU operator would not make too much sense here. So we're still using a sigmoid, but it's the same form as a standard neural network, except that we have this bottleneck. So we can train this network. So that means that we train all the weights of the different layers. And so this thing is an embedding of the pose of the hand. So that's what we can get. And now we can cut this network here and replace so the beginning by the previous network. And so now, instead of predicting the pose directly, all the 3D location of the joints, we will train the network to produce the embedding, so the small vector that represent the pose. And the good thing is that we can plug these two networks together, and so we get just one big network, which is optimized in two steps. One step to optimize the last part, so the embedding, and the first part, which is the prediction of the embedding. And actually, the optimization in two steps like that works much better than the optimization of the full network. So we could start with this network and do the optimization, but actually it does not work that way. And actually, it doesn't work at all. It gets stuck to a local minimum. So sometimes you have to apply some tricks to do the optimization. And so with these methods, we can fix the previous pose. So we can predict natural process. And so with that, so we can be better than the state of the art. So one thing which is interesting to notice with this embedding, so there is actually this bottleneck, and so the autoencoder network, so this one with the bottleneck, is actually very close to a PCA, so to a principal component analysis, because it reduces the dimensionality of the input. And anyway, with only one layer in the middle, it's mostly a linear projection, so maybe there is a sigmoid, but it's still almost a linear projection, and which is very close to a principal component analysis. And so we actually initialize the autoencoder with the matrices of a PCA. Otherwise, actually, it does not work very well. What is interesting, or what is surprising and interesting in practice, is that we don't need to tune the dimensions of the embedding, and at least when we use the PCA for initialization, because that was very surprising to me, and I needed some time to understand. Or at least I think I understand what's going on now. But so that's on this axis. That's the dimension of the embedding, so the dimension of the eigenspace. So if we use a principal component analysis, and that's the average error over all the joints. And what I was expecting is that there would be a sweet spot, an optimal dimension of the eigenspace. So something. I was expecting a curve like that. But it's not like that. There is a plateau, and the performances keep, or they don't keep improving, but they stay the same after some point. Why I was was expecting like that, and actually, even when we use the full dimension, all the dimensions, it's better than the without the embedding. So which is a bit surprising. So the point of the embedding was to learn a compact representation. We don't have this compact representation there, but we are still better than this the performance without the embedding. And so actually, what's going on is the coefficients in the embedding are very small at some point. So after the for the last dimensions, and the CNN learns to predict very small coefficients for the last dimensions. And that means that we don't have to tune the dimensions of the embedding space. The CNN learns to predict zeros or very, very small coefficients for the last dimension, and then it doesn't matter. So in practice, okay, so that's a bit surprising, but in practice that's interesting because we don't have to tune these dimensions. So it's 11:15. That's
5 minutes more.
5 minutes. Okay. So yeah. Okay. So we'll. Yeah. So the best thing to do is probably to present so the second part of the algorithm, which refines the position of the joints. So far, the prediction of the network is the full pose, and so we try to predict all the joints all together. But that's it's relatively difficult to do because it's everything all together. So the next step of the algorithm is to try to refine the position of the joints independently. So we get a relatively good initialization or good estimate with this first network, and then we try to refine this position. So we can do that. The first thing that we tried is to do this refinement with the standard deep network. So now the input is a small image, so part of the image, a patch of the image, which is centered of the joint, of the prediction of the joint from the previous network, so what I just presented. And the output would be 3D displacement to correct for the position of the joint. So something that will move the center to the better estimate for this joint. And the problem is it was not working at all, which is a bit annoying. And actually, so the reason is these layers, so the pooling layers. And if you remember, the pooling layers decrease the resolution of the images, which is useful. So to decrease the dimensionality of the problem, and also to get to be invariant to small shifts in the image. So when you do object recognition, for example, that's very useful to be invariant to the small shifts, except that here we don't want to do object recognition. We want to predict a very accurate vector. And so all these layers, so the pooling layers, hurt us. So we could remove them. But if we remove them, then we don't decrease the problem anymore. So that we keep working with very large vectors all over the network, and it's untractable. So it's very difficult to deal with this large data. And so what we did is basically a mix of pooling layer and so network with pooling layers and a network without pooling layers. And so we use a first large patch that try to capture the context of the joint. And here we use a pooling layer. And then we also use a very small or smaller patch that which capture or tries to capture accurately the surrounding of the joint. And then we don't use a pooling layer. So because we start with something large, but we have a pooling layer, we get something which is tractable, and here we have a small region without pooling, and it stays tractable. And so we can use these different inputs all together, and we get a network which has this architecture. But if you remember, we are pretty flexible. We have the algorithms to optimize this type of network. And so the input is multiple. So we have different sizes. There is different branches in the network, and we can combine all these different inputs to get a better state. And so it helps to get better pictures. And just to show you some examples, so we get nice or more accurate localization for the joints. And just to give you an order of magnitude for the training and for the running time, so the training takes a morning or an afternoon, so a few hours on just a good computer. So we need a good GPU because everything can be done a lot of things can be done on the GPU, especially the convolutions. And at runtime, it's very, very fast. So it's nothing. We just need to apply to do a few convolutions, and it's amazingly fast. And actually, so the refinement part is not optimized, so we can try to do better. But okay. And okay, so. Yeah, so as a conclusion, so I know some people are still reticent to use deep learning, but you will do it in a few months. You'll see. So that's okay. So that's just for the conclusion. So that's just an overview of the different networks that we use. So it's as I said, it's a very flexible tool. You can play with it. You can adapt it to your problem. The drawback is that you need a lot of training data. That's the next problem, to be able to generate or to generate training data, to have better ways to generate training data, or to be able to train networks with less training data. But it's a pretty powerful tool. And yeah, so I will stop here. Thanks for the intention, and sorry again, I was so late, but I will be happy to answer questions.
Question? Some of the deep learning experts, okay?
I'm not a deep learning expert at all, but I had some questions about it because it's interesting. I like to use it. Can you go to the slide when you have this? Would you expect it to have a minimum but you didn't have it?
Yeah.
And you have a plateau. In there, I couldn't see why you would expect a minimum, because you're doing two things there. One thing with embedding, you are restricting to feasible configurations, right?
Yes.
That are compliant with the kinematic constraints of the hand. So if you are constraining to that restriction, then you will have better results than without embedding. That's one thing. And the other thing is just a dimensionality problem. Mm-hmm. If you use all your data, you will have better results than if you do not use all your data. So that's why I expect that they have the best results using all your data, mm-hmm, and constraining to kinematically feasible results.
But actually, there is no at this point there is no actual constraints anymore, because the network could predict anything. So there is no hard constraints in the network, and it could predict locations in the eigenspace, mm-hmm, which is very far from a correct pose.
Then I did not understand very well the function that you use to do that constraining.
So there is no constraint actually. It's really a prediction in the eigenspace, but you know that's maybe the data. So the data is supposed to be a Gaussian distribution or whatever, and so you hope that you predict some pose in the Gaussian distribution, but there is no thing that prevents the network, at least a priori, mm-hmm, to predict a point which is there, which has nothing to do with the physically possible pose. but so that's why if the eigenspace is small, then you are more or less guaranteed. Actually, it's not that. Even that is not true. To predict pose in the embedding space that's going to generate a correct pose. But when the eigenspace is too large, you can still predict a point which is very far away. So and there is no constraint. Actually, that's probably one of the problems in the with CNNs is that it's very difficult to impose hard constraint. Or I'm not sure there is a good solution. But the good thing is that because all the training samples have the last coordinates equal to 0, the network learns to predict these last coordinates or as 0. So that's my.
Okay. Yes. Yeah. Okay. So there are no hard constraints. You just use the projection,
exactly. But we just hope that's going to it's going to work.
And the other question that I had is when you do this thing that reducing dimensionality to have this this embedding and then going all the up again. Now you have much more dimensions in the final state vector. And
no, it's the.
In that.
So here, no, it's exactly the same. So the input, so the output is supposed to be the same as the input. So of course it's the same size. So it's the same length.
What is the last part here? What is it giving in terms of learning? Because you have reduced the dimensionality already. Now you have a larger dimensionality. But
so it's because we are going to keep only one part of the network. Actually, the second part of the network, because we are going to predict in this vector.
Yes.
And so the point is to learn to generate an embedding, basically. So it's like you can see that as a generalization of a PCA with the network. But so here actually we used just one layer, so one layer in the middle, but you can use as many as you wish actually. And we tried to make the things more complex, but it was not really happy. So and actually the PCA works as almost as good as the thing, which is a little bit more complex because it has a non-linear operation, and the PCA is so we initialize with the PCA, then we do a refinement, but it's almost the same. We just create it.
Thanks.
Another question about this. Are you alternating between this optimization, so the Autoencoder one, and the one for actually estimating the pose, or are you using the two objectives at the same time?
No, it's just to be clear.
Sequential.
So it's a separate optimization.
Okay,
so
so
we optimize that first, of course.
And then you use the weights.
And then we train that to predict this thing. So then we can do a refinement of the two networks joined together, but so to predict the correct pose here. But it was not really improving much. It was already in a local minimum. And we try to do the optimization of the full thing, but so directly without these two separate optimization, but it wasn't working.
So if you train the left part of this network, you fix the last two layers.
Yes, exactly.
Okay,
And then we can optimize everything together once we are doing the estimate for the first part. But that's
I have a question. Just to clarify, you have already mentioned most of it, but I want to be exactly sure. It's about you're actually using this last layer to sort of denoise the output, right?
Not
sort of.
Not really denoise, because it's not. It's more a change of coordinate system. It's like a PCA. So
okay.
It's a compact representation, but we already discussed that the compact. It's not necessarily a compact representation, but at least it's another coordinate system.
Okay.
So it's more or less a linear transformation.
Okay, so this transformation is not actually a denoising. I mean, this autoencoder is not a denoising autoencoder.
Yeah, I would not call that a denoising. Yeah.
Okay. You didn't use noise in the training or anything like that.
No.
Okay.
There is probably You know, PCA also is some kind of, or can remove the noise sometime. So especially for for images. But I wouldn't, it's not the main point.
Okay. The other thing is that you mentioned that you also try to use several layers for the autoencoder, and also different initializations for the layers, right? You tried using something like ICA or other type of
no, we didn't.
Okay.
Maybe, I don't know.
Yes, because well, having only one layer, it is very clear that a linear transformation would be easy to find, because the network wouldn't have to move too far away from the initialization point.
Yes,
to have
initialize with the PCA.
Exactly, but perhaps having a more complex.
Another initialization would work at least as well, or better. I don't know. I suspect that the PCA works pretty well for this kind of problems, so I'm pretty sure that people try, at least, so maybe not exactly in this context, but to use ICA for dimensionality reduction for this sort of problems, but PCA is still probably a good option.
Okay.
Let's keep it here and switch to the other one, right? If we have more questions, then maybe in the ICA we can talk about some patterns.